Okay, good afternoon. I know you guys have been studying this retaining wall, but let's take a break. Today we are going to talk about slope stability. Why? Because we are going to start the slope stability project. Yes.
Can you speak louder?
I'll do my best. Okay. So for slope stability, the idea today is to explain you guys what the project is about and explain you guys how the software is working. So first, what slope stability is about? Basically, what we're doing with slope stability is we are assessing the equilibrium of any slope. So this is necessary for the design of slopes, for the stability assessment of existing slopes, and for the study of slopes that have failed. So in order to understand something about slope stability, first keep in mind that this is going to be a complete chapter in this class, in this course. It's chapter 4, so Dr. Cascante is going to explain very well everything about slope stability. We're going to give you just an introduction. Okay, so first we're going to review something about the types of slopes, the failure mechanisms, causes of slope failures, analysis or analytical methods, and step by step, we're going to review the process of slope stability analysis step by step. And finally, I'm going to show you the software. So first, this is the difference between natural slopes and artificial or man-made slopes. So the first ones is like valleys, hills, coastal slopes, river banks. The second one is like excavations, embankments, trenches, open pit mines. In this case, for the project, we're going to do something like this, which is excavation for the foundation of a building. So just to keep in mind, this is artificial slope. So this is what we're going to do for the project, okay? So, in order to understand the slope stability analysis, we need to know the failure mechanism and the failure surface. So, to understand the failure mechanism, we're going to follow this classification presented by Barnes. Dr. Barnes presented this 40 years ago, and this is still very widely used around the world. So first, two things: type of movement and type of material. We're dealing here with the type of movement, which is a rotational movement. Okay, so there are 7 different movements. Dr. Cascante is going to explain this in more detail, but what you guys have to know now is that for the slope stability project, we are dealing with rotational movement, which is basically like this image here. So we have one mass of soil moving, rotating with respect to that point A. Okay, that is basically what we're going to do for this project. So, and the material we are going to use is basically soils and predominantly fines. So we are going to have an earth slide. That is what we are going to deal with. Okay? So what are the causes for slope stability, for slope failures? So first, something like 1 century ago, Dr. Felenius presented that idea for factor of safety. Factor of safety is defined as the available shear strength divided by the induced shear stress. So if we think about that, the lower the factor of safety, the less stable is the slope. So the internal causes and the external causes is that like differentiation, it's like trying to differentiate what causes are associated with the shear strength and which ones are associated with the shear strength. The internal causes are related with the decreasing of resisting forces, so that means the shear strength, okay? And the external causes are related with the increasing of driving forces, that means the shear stress, okay? So just for you guys to let you know that we have to consider this increasing pore pressure or seepage forces or sometimes the progressive decreasing of cohesion. For this project, we are going to deal with this pore pressure, with these seepage forces, and maybe with this steepening slope angle. Of course, with the increasing loads, we are not dealing with rainfall or erosive process in this case, but for increasing loads, there are static loads and pseudostatic loads, okay? For the earthquakes, we are considering a pseudostatic analysis, okay? We are not dealing with dynamic analysis, which is different, okay? So next, the analytical methods. There are like two kinds of methods. The first one is the limit equilibrium method, and the second one is are the numerical methods. In this case, we're using the limit equilibrium method. We are not using finite elements or finite differences for the slope stability analysis, but we could use finite elements to try to simulate the behavior of the groundwater. We're going to see that in the software, but not for the slope stability. For the slope stability, we're going to use the limit equilibrium method. So there are infinite slopes, like natural slopes, or finite slopes. And for finite slopes, we could do analysis in total stresses and analysis in effective stresses. Okay. For the project, keep in mind that we are using limit equilibrium method, we are using a finite slope, and we are using effective stress analysis. Okay? So, in order to do the slope stability analysis, we are going to use this ordinary method of slices. So, have you guys read the document for the project? No? Okay. The idea for the project is that you guys use the software, and you don't need to know or to understand very well this method in order to use the software right now. So that is why you can start using the software now, but at the end you guys have to do some numerical hand calculations. And to do hand calculations, you guys have to use this ordinary method of slices. That is going to be presented by Professor Cascante in chapter 4. So the idea is basically that you assume a failure surface, and you divide that surface in slices, and then you analyze the forces acting on that slice. Keep in mind that these methods are not 100% accurate, meaning that some of them are using equilibrium of moments, but not equilibrium of forces. Some of them are missing, for example, the forces interacting between slices. But you're going to learn more about that. What you guys have to keep in mind now is that this is the method the software is using, basically. It's taking the surface and dividing slices, analyzing the forces, and comparing that forces with the shear strength in the soil. So why is the method called limit equilibrium? The method is called limit equilibrium because you do that many times. You guess the first failure surface, and then you change the surface. And so you get an over factor of safety. If you do that 100 times, 1,000 times, then you could get a minimum, and that is the limit. Okay? The software is doing that. The software could do that. Could do 6,000 analysis in 1 minute or something like that. So that is why it's so powerful. So What is the process for the slope stability analysis? First, we're going to define the slope, then define the failure surface, define the scenarios of analysis, and review the safety criteria. So for the slope, this is what we have in the document. So this is the initial condition. It's like we have a semi-horizontal land terrain, and we have two boreholes. We know that there are something like 5 layers, different materials. The idea for this project is that you guys understand how to do some interpretation of those boreholes, and then how to apply that to create this model. So the software these days is much better than before and is allowing you to do that automatically. But for the hand calculations, you have to do it, okay? So let's start by reviewing this borehole information. You guys have 2 boreholes, okay? For this borehole, what is important to keep in mind is the first thing, elevation, ground elevation, okay? The second thing to keep in mind is the materials, like we have field, sill till, clay till, sill till again, and the bedrock, okay? So that means 1, 2, 3, 4, 5, and the bedrock, okay? So then, if you compare this borehole with the second one, you could see that the materials are the same, but the thickness of the materials is not the same. Okay? So the idea is to connect the 2 boreholes to create the layer. Now, this is the initial model we could consider. We could consider these are X and Y coordinates. If we consider the model is starting at 60 meters in Y coordinate, this is X and Y, and this is 0. The model is here at 60. Okay. So the idea is that the surface for the model is at 80 meters. But in order to define the surface, the real surface, we need to consider the elevation for this borehole and the elevation for this one. So you see the elevation in this case is 80.45. So that means 45 centimeters above this surface. And for the second borehole is 78.71. So that means something like 1.29 meters below this surface. Okay? We're going to do that in the software. And then we're going to connect the points to create the layers. So we have here the field, and here the same material, you see, field. So this is what the information we need to consider in order to define the geometry of the model. The second thing to define the model is the properties of the materials. So we have here information coming from the lab and field test. So we have the characterization of all the materials we need. Actually, we have one. We are not going to use this clay, but because there was a clay in another borehole, it's already characterized, but we are not going to use it. But we have here dry unit weight, water content, total unit weight, specific gravity void ratio, saturated unit weight, friction angle, permeability, and cohesion. All these are effective parameters. Okay? So we are ready for this part of the model. We have now defined the slope. Now we are going to consider the failure surface. To consider the failure surface, we have many options. We could do it with circular surface, perfectly circular surfaces, or with this kind of wedge, or with this kind of irregular surfaces. So we say this is rotational because the principal component of the movement is rotational, but that doesn't mean that the surface has to be always circular. However, circular is the easiest one, and we are going to use circular surfaces for the project, okay? Now, we are going to consider the scenarios. All this information is explained in the document I mentioned before. For each scenario, keep in mind you have to consider the loads, static and pseudostatic, the groundwater, and the slope inclination, okay? So for the first scenario, what we have is we are going to build or to construct a new building in this area. So we have to do some excavation in this area, but consider that we have this existing building and we cannot touch that building. Okay, so the excavation is supposed to be 12 meters depth, average, not exactly, but about 12 meters depth. So because 12 meters is too much for just one step excavation, as we are proposing, the excavation is done in 2 stages. The first one, 6 meters, the second one, another 6 meters. So this is the idea for the first stage of the excavation. So your assignment of the project is basically to define the inclination of this slope. Okay? It's not that difficult, but it's challenging in the sense that you have some constraints for the model. So this is the second excavation. Okay? So for the second part, you have to define now this is not. Okay? But now there are some constraints, and the first, let's think about this. So first, we have to consider here in this area the load due to the existing building, which is 40 kilonewton meter square. Then you have to keep in mind that you cannot move these points. This point is basically defining where the new building is going to be constructed. This is the area where the new building is going to be. So you cannot move this point. And this distance is the minimum distance you are going to keep for the excavation step. So this is what we're going to do at the end. Okay? We're going to have these buildings, and then we could fill this area and compact it. But that is not in the part of the project. Just the slope stability is what we are interested in now. So the criteria for safety is that the slopes you are going to design have to accomplish this factor of safety. 1.5 for static condition and 1.1 for pseudostatic condition. Okay? So this is the document I was talking about. Okay? And the document is very well explained, everything about the project. If you guys read the document and you have any question, please email me. I will answer any question. So basically, we have the boreholes report, we have the shear strength parameters for the soils, and we have now the geometry definition for the 3 scenarios. Then there is an explanation step by step about what you guys have to do in order to use the software, the slide. So the geometry is well defined. Then there are an explanation about how to define the project settings in order to perform the analysis we are interested in, and then how to introduce the data. Okay? Then you guys have this step by step for hand calculations. Okay? So let's do, is there any question now? No questions? So let's use this software, Slide. So you guys go to the lab. Yes?
Does Slide have have like a manual or something that does explain?
Yes. I'm going to show you. Here we have Slide, and the Slide has tutorials in here. Okay? So there are tutorials for different things, but what I'm going to explain today is like the basics, step by steps, in order for you guys to understand how to use the software. So you guys basically could skip this tutorial review, because I'm going to explain how to use the software, but it's a good idea if you check the tutorials if you want to learn more about the software. Okay? So in this slide, we are going to create a new file. Okay? So let's save this. So the first thing we are going to do with the slide is to define the project settings. So here we have in the document, I mentioned something about the project settings. So we are going to the software analysis, project settings, and we are going to use, the first option is the general option. So if you check my problem, if this is going to consider a rotational movement, the movement is in that direction, okay? It's going left to right. So we have to consider that to define the first thing here, the failure direction, okay? So we are going left to right. Okay, this is basically the only thing we need to change here. Then we go for soil profile. And this is a very nice thing in the software, because now we have, for the soil profile, we could include the boreholes, and the software is creating the model automatically, okay? So for this use soil profile, we choose this one, and we create settings. So the software is asking me about how do I want to interpolate between boreholes. We are going to do it linearly, and we are going to interpolate the top surface because we have the elevation for the boreholes. Okay, then we have scenarios. So you don't have to create many files, just one file but different scenarios. So we are here considering multiple scenarios. Methods, let me see here. I'm recommending, for the methods, I'm recommending ordinary, GLE, and Bishop. Ordinary, Felanius, GLE, and Bishop. So you see there are other methods. In this class, in this course, you guys are going to be taught about ordinary method and Bishop method. So at the end you're gonna know how this method works. Then the number of slices. You could use here 100, and then the groundwater. For the groundwater, we are going to use one option, which is the finite element analysis in order to do steady-state analysis. I'm going to show you that. And then no more. That is all we need to define for the project settings, okay? That's it. So now we are going to define the geometry. So first thing, create the external border. For the external boundary, so we know the coordinates. And you see this little box here, down to the right. So basically it's asking me for coordinates. As I know the coordinates, because I gave you the coordinates, these are the coordinates. I could create the external boundary very fast. Okay. So you see this is my surface is at 80 meters. Okay. Now we're going to include the profile. So the first thing we're going to do is to include the borehole's information. So let's include the first borehole. The first borehole, the name of the first borehole is going to be this one, for example, A2210. A2210. The horizontal X location is given in here, is at 10 meters. And the borehole top elevation is what I was telling you guys, 80.45. Okay. And then we have one layer. So we need 1, 2, 3, 4, 5, 6 layers. 6 layers, okay? The first layer is this material, fill. Okay, we could change the names after. But what is important here is that you guys come to the borehole, measure the thickness of the material, and include that information in here, thickness. Okay, I'm not going to do it exactly. Let's say this is 2.5 meters. You guys do it with the real information. The second one, let's say, is 1 meter. The third one, let's say, is 1.5 meters. Then it's something like 3.5 meters. And then another 1.5. Okay? Oh. So this is 10. Let's say this is 10 meters. Okay? This is how you create the first borehole. You see? The layers are now horizontal because we have just one borehole. Now let's include the second one. For the second one, the elevation is different. The elevation for the second one is 78.75. and the horizontal location for this second borehole is 40 meters. Okay? And let's change something here, for example, 1.5, 1.5, 2.5, 2.5. Let's do this. Okay? So now you see the layers are not horizontal, and that is the real condition. Okay? So that is the profile, and we have now the geometry and the materials. But now this first polygon is going to be excavated material, because we don't want this material to be, okay, there is an option to remove that from the profile. With this option, we excavate that material, and now we have a real condition. And this is the geometry. So now we are going to define the materials. For each layer, we have the properties. The properties are given in this table. So just come here with the right click, material properties. Okay? And then you could change the names. For example, for the first one, we're going to see this is the first one is the bedrock, for example. The second one is it's okay if I turn off the light, please. So for the first one, we have, okay, the properties. For the bedrock, so we have, in this case, we're going to include total unit weight, cohesion, and friction. Okay? For the bedrock, we have 23.6, and we have a cohesion of 918 kilopascal, and we have a friction angle of about 36.93 degrees. Okay, so then, oh, sorry. The second material, okay? Any question? So following the same process, you could define the properties for all the materials you are considering. In the profile, we have, in this profile, we have fill, silt, so we could say the first material here is going to be fill, the second material silt, the third material siltil, then clay till, and finally the seal till again. Oh, it's the same material. You see this material here, the third material is also here after the clay till. Okay, so we don't need to define once again this material. Okay, it's the same material at the end. Let's say this is a clay that we are not going to use. But now we have the properties for the materials. Any question about this? This is maybe the most important part in the project, in the software. If you define the properties in a good way, everything is going to be okay. If you put crabbing through there, whatever you get is not useful. Okay, so if you guys have questions, let me know. Yes?
So maybe you were about to go on to this anyway, but how do you now put silt till and apply that to two different layers?
Okay, so this is to define the material properties. There is another option which is assign material. So here for the first layer we have fill. For the second layer we have seal till. For the third layer we have, for the second one we have seal. For the third one we have seal till. For the fourth one we have clay till. And then we have once again the seal till, like that. Okay? So now we have now we have the material definition. So now we need to modify this external boundary in order to move it to the real topography profile. Now we have the first part of the project. This is the profile, okay? What else we need to include in here? We need to include the water table, we need to include the loads, and we need to start with the excavation. So for the loads, there is an option here, loading and support. Here, we are going to include a vertical load with this icon here, vertical load. And for the vertical load, we are going to use 40 kilopascals. That is explained in the document. Okay, and this vertical load is going from 0 up to 10. You could do it by hand, like this. A good approximation is a good idea. The other option is to include a vertex, like this. Modify the geometry, include a new vertex, and this vertex is going to be 10 and 80. And then apply the loading between the initial vertex and the new one, like this. Okay? Any question? We have now the load due to the surrounding building. This is the existing building. Okay, now we need to include the water table. Because we are going to use finite element analysis to simulate the groundwater flow, we need to define a new boundary, which is where the water table is, or where the water table was when the boreholes were drilled in the field. So for this project, there is here in the table of the properties, you guys could see here, for each borehole we have the elevation, we have the water table depth. So for each borehole is different, and because each borehole has a different elevation, so you guys have water moving from one side to the other. And the elevation of the bottom of the excavation is also defined in that table. So let's include the water table in here. In order to do that, we are going to include a new boundary, let's say, assuming that we were going to include like a new material, okay? So for that boundary, for the water table we have 2.5 and 3 meters. So we have one borehole in here, one borehole in here. The water table is 2.5 meters at this point. And yeah, 3 meters at the second point. So the water is like going like this. Okay? So we are going to include this as a new boundary, just because we needed to define the boundary conditions for the finite elements analysis. So here in the software we are going to consider this new boundary, and let's say you guys have 10, because we know that the elevation is 2.5 meters below. Assuming that the elevation of the borehole is 80, the elevation of the water table is 77.5, but the elevation of the borehole is different, okay? So just in this case, for example, I'm going to consider that, but you guys consider the real elevation for the borehole, okay? And the second borehole has 40 meters in X direction. And for the second one, I'm going to consider 77. But you guys consider the real elevation, okay? So that is a boundary we are going to use for the groundwater, not for the materials, okay? Just keep in mind that. Now we extend this boundary here from this point to the initial point in the model. Okay, what else we need? Now we are going to do first static analysis. So we are not going to include now the earthquake parameter. So this is what we need. This is the first step. Then we are going to start with the excavation. Okay, so in order to do that, let's include some of these vertices here at the surface, anywhere, because they are going to be useful for me to modify the excavation. So we know the constraints for the geometry. Here we know that we cannot move this point. So let's define another surface to keep in mind this boundary. So 30.68 is going to be my starting point. So I'm going to include another surface, 30.68. I'm going to take it up to the end. Okay? So now this is my initial model, and then we need to create another scenario. So we are here creating we are going to add a new group. The first group is the initial condition. Okay? Initial. We are going to include a new group, which is going to be the stage 1. Stage 1, and then stage 2. Okay, for initial condition we have this static analysis, but also we are going to have another scenario, which is, if you see, when you add scenarios, you are sharing the geometry, materials, whatever you have defined is exactly the same. But for this second scenario, let's say the first scenario, we are going to call this first scenario static, and the second one pseudo-static. So for the pseudo-static scenario, we are going to include the earthquake parameter in here with this icon. Okay? Then it's going to be 0.2 in horizontal. Vertical, we are going to consider 0. Now we have one scenario for static, one for pseudostatic, and this is for initial condition. Now for the stage 1, we are going to consider this static, and you could repeat the process: pseudostatic for stage 2, static, pseudostatic. Okay? Now for this scenario, we are going to profile geometry. We are going to define exactly the same. 0.60, 50, 60, 50, 80, and 0.80, and close. Okay, then we have the same geometry, the same materials. We don't need to define anything again. We now have two scenarios, and we have different stages, and we are going to start with excavation in this stage and this scenario. So for that scenario, we are going to add these vertices. Oh, we need to include here the boundary. Remember this one, which is 3068. Okay. So this is the constraint for the excavation. So now we add some of these boundary vertices, and it's very simple. Okay, let's do it for the stage 1. Elevation for stage 1 is 74 meters here. Let's do it for stage 1. So we add this surface, let's say 20, 74. And then we are going to use these boundaries these vertices in order to modify the geometry of the surface. So we could move the vertices here. Something is wrong with this. Move the vertex, and it's as simple as this, and that is your excavation. Okay? So now you guys have the excavation. Let's say this is my first stage for the excavation. We are missing here the load. So let's add the horizontal load, or 40 kilopascal, from 0 to 10, approximately 10. Okay? So now we have the first slope. How are we going to analyze the slope? So go back to the explanation and check. What we have to do is to define now the failure surface. Okay? For the failure surface, there is an option here. It's a complete menu, surfaces. For surface options, we're going to select circular surface. Okay? And we're going to check this one, which is create a tension crack. Okay? That is going to be explained in the class, but it's basically in order to avoid the software to create a reverse failure surface. So when you create a tension crack, you see the difference? This is a reverse failure surface. When you create the tension crack, the failure surface is going vertical. And the second thing we're going to do is, let's consider a minimum depth of 1 meter. So that means if you have a failure less than 1 meter, you are basically not considering that failure surface, okay? You are neglecting that surface because 1 meter is not too much, so it's not really important. Okay. Then the second step for the surfaces is, now we have to define, if you remember here, I was telling you guys about the ordinary method of slices. So we have to define this point, the center of the circular surface. But for the software, we have to define many points. So in order to do that, we define basically a polygon, and we ask the software to look for different surfaces with center in different points of that polygon. So come here and include here in surfaces AutoGrid is the most easiest way to do it. Oh, something is missing here. Analysis, project settings. Somehow this is going in the wrong direction, okay? And then surfaces, AutoGrid. And let's take here 100 points in X direction and 100 points in Y direction. And let's extend this something like this. So when we define 100 by 100, we are asking the software to do the analysis 10,000 times. Okay? So now we could do the analysis for the water table. Okay? So we have the first part defined. Now let's consider the water table. So for the water table, we were considering another boundary. If you remember, we were defining the boundary something like this, just in order to define the boundary conditions. What we are going to do here is we are going for a finite element analysis. Have you guys ever done something like that? Okay. So don't worry. The only thing you need to consider now is boundary conditions, which are very easy for this case, and the parameters for the permeability for each material. So come here to the groundwater option and ask the software to create a discretization for this model. Okay? Is that easy? Then for this surface we create before, we are going to define the boundary conditions. And the boundary condition for this surface, for this boundary, is going to be zero pressure, meaning there is the location for the water table. Okay? And then there is one, oh, we have to go back because I forgot something important. And that is that in the document, there is one part when it is explained that for safety reasons, the water table should be below the bottom of the excavation, at least 1 meter below always. So we need to define another boundary in order to define to consider that option. Yes, so if this is 2574, let's say 2573. So that is 1 meter below. That boundary is going to be useful for the water table. Okay, so let's go back, groundwater, discretization, and now we take this and define zero pressure. Okay, so we have two boundaries here. You see the first part and the second part. We are not defining any other boundary, and we are not defining this part of the water table. Why? Because we are expecting the water table is going to change, and so it's going to flow the water from this point to this point, and the software automatically is going to create the water table. Okay, so then we have to go with the right click and define the hydraulic properties. Okay, so the hydraulic properties are given in the table. Everything is given. You guys don't have to look for any parameter here. So you guys see here the permeability. So just use these values for the model. Include those values in here for every single material. Okay. I'm not going to change the values now, but you guys are going to do it. And I'm going to get now the results for the water table. So you see, this is my water table, and that is the one I'm going to consider for the slope stability analysis. Any questions? Yeah.
So for the component of the water table surface on the left that we've defined, that was the original one. How do we know how far to extend that?
You could do it 10 meters, 12 meters. It's not that.
That doesn't change like the slope stability?
It could change a little bit, yeah. But if you see what we are interested. Okay, let me finish and you will see the answer to your question. Okay, let me go back and then go to, you see when you are doing finite element analysis, you have here steady state groundwater, so you go back to slope stability. You could change these options. Then because we now have the results for that part, then we could perform the slope stability analysis. So I'm going to show you the failure surface. Oh, this is really bad. 0.5. Really bad. So you see, in this case, for example, the failure is not affected by the water table. Let's see, for example, oh, not this one, this one. Let's see, for example, if we consider this one. You see, if we extend this water table a little bit more, it's going to be different. But it's okay. I'm considering the water table is up to 10 meters. That means below the existing building is horizontal, and below that and further, I'm not considering the other points. So the software is defining the water table. But of course, the shape of the water table is going to be different because I'm not changing the properties for the hydraulic properties for the materials. But once you do that, it's going to be completely different, okay? So it's okay, it's not a problem. If you take 10 meters, 12 meters, it's not a problem, okay? Whatever you are doing, just explain it in the report, okay? So now we have the result. So as you can see here, we have a very low parameter, very low factor of safety, 0.48. So that is where your ideas are welcome. How could we improve this? How are we going to do it? So the first thing that we usually do is to modify this inclination of the slope, okay? So in order to do that, we are going to modify boundaries here, okay? And with boundaries, we are going to change the slope angle, okay? When you change the boundaries, you're changing everything related with the groundwater. So you guys have to go back and repeat the process and then do the analysis, the slope stability analysis again. Okay, so we are considering here that we are going to change these boundaries, change slope angle from this point to this point. So these are the options to change the angle. Let's use the horizontally projected displacement, and we are going, for example, 5 degrees to the left. But 5 degrees maybe is too low because we have 0.4 for the result. Let's do it with a more aggressive change. Let's consider, for example, 15 degrees. Okay. So if you guys see what is happening, is that now the boundary is rotating in this direction. Okay. You see? And that is what you're going to do. That is all the project. Just play with the options for the inclination of that slope. Then once you accomplish the factor of safety, 1.5 for static conditions and 1.1 for pseudostatic, then go for the second stage of the escalation and repeat the process. Do the same. And then, for sure, what is going to happen is that you guys are going to have what is going to happen is that you guys have the first slope for the first stage. So you find the failure surface and you say, this is my factor of safety higher than 1.5 for static condition. So then you come for the second one. You know this distance has to be 3 meters. Okay, then you come for the second stage. Then when you modify this slope, for sure, this distance is going to be modified. So then you have to move, because this could be moving this direction, this direction, this direction. Okay? So you guys have to play with that option, those options in the software. And that's it. At the end, you guys save the file. I need you guys to submit that file with the report. The file is going to be more than 25 megabytes. So it's okay if you submit the link, OneDrive or Dropbox or whatever. Okay? So what do we need for the report? For the report, we need basically these contents. Dr. Cascante asked me to recommend you guys this. I don't know that because I haven't used it before, but most of you guys know that guidelines. So use it for the final report. And the contents are presented in the document. It's already posted, which is already posted in the website. So basically we need a problem description, and the problem description is already given in the document. The background information is also given, which is basically the boreholes, the material properties, the location of the boreholes. Yeah, it's basically the proposed solution is basically this. The inclination of the blocks. Okay? And what is the main conclusion? Okay? You guys have to do some git review and numerical model verification. So once you have the results for the software, you are going to have, oh, let's do it in the software. You're going to have this failure surface, okay? Oh, we change it, okay. Let's do it fast. You guys use AutoCAD, right? AutoCAD? Okay. So for the hand calculations, that is going to be really useful. So we modify 15 degrees, and we got now 0.85 in the factor of safety. So we are close, okay? But what is important here is to see this failure surface, okay? Okay, this is a very shallow surface, but let's think about this surface, for example. If this is the surface, you got at the end with 1.5 or whatever, okay? So what you guys have to do now is, for the hand calculations, is to create a boundary here for that surface. Use this tool to create that boundary. So you could approximate the failure surface like this. And then, okay, you guys could do it with better, okay, whatever. But at the end you got this. And you could export this polygon to DXF, okay? Export to DXF, okay? So we have now the failure surface. And with that failure surface, that is the one you're going to use for the hand calculation. So then you consider that surface. Where is the surface? So that is my surface. Then you divide this into slices and use that surface for the hand calculation. Just one surface, okay? That one. And compare the result with the one you got in the software. If the software is giving you something like 1.5, so how much are you getting with your hand calculations? Okay? And you could then get some conclusions about what is happening, why is different. You guys are considering 3 different methods inside the software, so compare the 3 methods. I don't know, okay? You guys do whatever you consider is okay for the conclusions. Okay? And explain the methodology you are using, which is gonna be explained in class actually, the equilibrium, and explain present the numerical results, conclusion, references, and appendices. And that is the project. Any question about it? Okay. If you got any question, email me. You guys know my email. So email me, and I'm gonna post this material in a PDF presentation in the website. So just for you guys to know it. Read the document. If you have any question about the document, let me know.
First slide, is there like a version of slide available for download by students, or do you have to use?
No, that is a full version. We got the full version of it.
Right, like, is the only way we can use it through the lab computers?
At least legally. Okay? Yeah.
Okay.
Okay, guys, thank you very much. Whatever we have done today is being to be posted in a video. The screen was recorded, so you're going to see whatever I have done in the software, you're going to do the same. You could see the same. Okay? Thank you very much.